Thank you. Good afternoon, and thank you again, Farooq, for the introduction. So this webinar is designed as an introduction to some of the privacy and security issues surrounding the contact tracing application, and in particular the exposure notification applications, COVID alerts. So we will look at how COVID alerts contact tracing application works in general, then move on to talk about the different privacy issue of the Bluetooth broadcasting and scanning behavior used in this application. Then I'll try to describe how the temporary exposure keys are generated, distributed, and stored. Also describe different privacy consideration in the key scheduling and different cryptographic algorithms that are being used in this kind of applications. And I will mention one possible security attack on this application, and at the end, we'll show that if we can trust this application or not. So there are three elements to COVID alert application system: the mobile app, the key servers, and the one-time code distribution process. User will voluntarily download the app from the Google Play Store or Apple iOS Store onto their devices and provide consent to participate in exposure notification process. So each device with the app installed is sending out and listening for random code called rolling proximity identifier, or short for RPI, which are not static. On a daily basis, the Google Apple layer automatically generate a random temporary exposure key, or TEK, and the TEK of a day then generate a new random ID, a new RPI every 5 to 20 minutes. And the RPI are not identifiable and are not accessible to the app or transmitted to this key server. The installation and opening of the app initiate the activation of the device Bluetooth function so that the device begins sending signals to and receiving signals from the devices of the other users who have downloaded the application. This Bluetooth communication between participant users is in a short range, device-to-device communication, and nothing is being transmitted to any server. The temporary exposure key are stored on a device, but may only be released to the key server in the case of positive test result and explicit user consent. When a user receives a positive COVID-19 test result, the provincial health authority who have adopted the application will provide them a one-time code, and the instruction on how to enter it into the app will validate the one-time code and ask the user if they would like their past 14 days of TEKs to be sent to the key servers. So after the individual consent, the TEK are sent to the key server, allowing other users they have come in contact with in the past 14 days to be notified once their app has downloaded on this case, and on a predefined schedule once every 4 to 24 hours, depending on battery level or when the application is open, the app downloads this new diagnosis key from the key server. So the app passes those diagnosis key to the GAOS layer, which is deployed by Apple and Google, and this layer regenerates the RPIs, or rolling proximity identifier, from each of these provided diagnosis keys. So I'm trying to describe very generally what is going on when a user using this application. So this layer, which is called GAOS, compares these generated RPIs to the list of locally stored RPIs it has encountered in the last 14 days. And if the GAOS layer finds that any of these regenerated and locally stored RPIs match, and the exposure notification risk criteria are met, these risks are like length of the exposure, strength of the signal, and the list goes on. The matching happened on a device, and the key server has no way of knowing if the two devices interacted. This was just a very general explanation of what's going on. So there are some exposure notification definition we need to know. At least I already mentioned 2 or 3 times the rolling proximity identifier and the temporary exposure key. Just going very fast, the TEK is generated every 24 hours for privacy consideration, and the RPIs is a privacy-preserving identifier derived from temporary exposure key and sending broadcast of the Bluetooth payload. So the identifier change about every 15 minutes to prevent wireless tracking of the device. And there is something called associated encrypted metadata, AEM. We will see in the next slide the usage of all these terms, and the privacy preserving encrypted metadata that shall be used to carry protocol processing and transmitted power for battery distance approximation, for instance, and this AEM change about every 15 minutes. So we are looking at the structure of the key and the way broadcasting and receiving the key are designed for this application. Exposure notification is a Bluetooth low energy service registered with Bluetooth special interested group. It is designed to enable proximity sensing of the rolling proximity identifier between devices for the purpose of computing an exposure event only. Device broadcast and scan for the exposure notification service by a way of 16-bit services, and the service data type with the service of UUID shall contain a RPI and AEM that will both change regularly. So this exposure notification service payload has 3 sections: flag section, complete 16-bit services, and service data 16-bit UUID. These bits are completely for purpose of for instance, versioning, like there are 3 bytes. Byte 0 is versioning, like from bit 7 to 6 is for major revision, from bit 5 to 4 is minor revision, like bits 3 to 0 is reserved for future use, and they have a byte for transmit power level, which this is the measure that transmit power of Bluetooth advertisement packet and is used for improve the distance approximation only. And the range of this field shall be like minus 27 to plus to 127. During this, and this is a broadcasting flow, during the Bluetooth broadcast, advertisements are to be non-connectable, undirected of type ADV. So the advertiser address type shall be random and non-resolvable. And on platforms supporting the Bluetooth random private address with randomized rotation time intervals, the advertiser address rotation period shall be random value that is greater than 10 minutes or less than 20. So it's a range between 10 and 20. And the advertiser address of RPIs and AEM shall be changed at the same time so that they can be linked. They cannot be linked. And if the hardware allows, a separate Bluetooth broadcasting instance shall be used to provide the reliability and flexibility in choosing optimal intervals. The broadcasting interval is subject to change, but is currently recommended to 200 to 270 milliseconds. This is the scanning flow. I'm just showing this, and I will go into the detail of in case a user is diagnosed with COVID-19. We are just going through every bit of design that they have in their procedure. They are very transparent in that terms, and that's why we can look under the hood. So in the Bluetooth scanning flow, discover exposure notification service advertisement shall be kept on the device. And as you can see, scan results shall be timestamps and RCCI capture per broadcast. And the scanning interval and window shall have sufficient coverage to discover nearby exposure notification advertisement within 5 minutes. And within 5 minutes, if they are in contact with them more than this, they will issue a flag for it and just consider it as one-time exposure, and they have measured about the exposure distance and the time. So the scanning strategy works best in opportunistic ways, so it's leveraging existing bakes and scan windows, and with minimum periodic sampling every 5 minutes. They have also a scan power consideration. It's like platform running the exposure notification service shall be designed to account for a large volume of broadcaster in public, and shall frequently rotate their random non-resolvable address and rolling proximity identity, and whenever supported by hardware and the operating system Bluetooth controller, duplicate these filters. Some of the privacy measures that we could observe in their broadcasting and scanning was actually interesting. And the exposure notification Bluetooth specification does not use location for proximity detection. It strictly uses Bluetooth beaconing to detect the proximity. So a user RPI change on average of every 15 minutes and needs the TEK to correlate to contact. So this behavior reduces the risk of privacy loss from broadcasting the identifier, and proximity identifier obtained from other devices are processed exclusively on the device only. They always need the user consent, and if diagnosis with COVID-19, that's a different case, which we will go into detail after this slide. And the user must provide their consent to share diagnosis key actually 2 times. So user have the transparency into their participation in this exposure notification system. Before we go into how they are what is the case when the positive COVID-19 case is revealed. We're going to just explain a basic cryptographic algorithm that they are using. So, and because they are very transparent, the whole algorithm can be seen from zero to the end. So what they are using is HKDF, which is a simple key derivation function based on hash-based message authentication code. And the main approach of this HKDF follows is extract then expand paradigm, where the KDF logically consists of 2 modules. The first stage takes the input key material and extract from the fixed length of pseudo-random key, and then second stage expand this key into several additional pseudo-random key. It can be used, for example, to convert shared secret exchange via very secure key exchange algorithm into a key material suitable for use in encryption. And for encryption, they are using an old but yet effective block cipher method called the Advanced Encryption Standard AES. The key size used for AES cipher specify the number of transformation rounds that convert the input into the ciphertext. So the number of rounds here would be 10 rounds for 128-bit. And as we can see, like AES has a fairly simple algebraic framework. And in 2002, a theoretical attack named XSL attack was introduced to show a weakness in AES algorithm, partially because the low complexity of its nonlinear component. So since then, the researchers have shown that this attack as original presented is unworkable, and basically AES can be considered as a secure and safe encryption method, especially in here. So to defend the privacy, this protocol leverages a new concept named Bluetooth pseudo-random identifier, referred to as a rolling proximity identifier. Each rolling proximity identifier is derived from lowering proximity identifier key, which is in turn derived from a TEK or temporary exposure key and decentralized representation of the time. So the rolling proximity identifier change at the same frequency as the Bluetooth randomized address to prevent linkability and wireless tracking, and non-user identified AEM is associated with the rolling proximity identifier, and the broadcast metadata from a user can only be decrypted later when the user test is positive. They even have the technical report showing every calculation for this. We can go into it later, into the more deeply into it if anybody interested. But some of them, like the EN interval number, which is a function to provide a number for each 10 minutes time window that's shared between all devices participating in this protocol, and this time window are derived from timestamp in Unix epoch time, and is fairly simple equation, which is timestamp over 60 multiplied by 10. This temporary exposure key roll at a frequent measure called the TEK rolling period, which is set to 144, achieving a key validity of 24 hours. It is only valid for 24 hours. And each key is randomly and independently generated using a cryptographic random number generator, and all devices sharing the same TEK rolling row at the same time at the beginning of an interval whose en interval is multiple of TEK rolling period. All right, so let's have a look on when a patient is diagnosed with COVID-19. So until here, all the broadcasting, scanning, storing reside on the user phone. All the communication, all the calculation reside on the user phone until but when there's a positive case. So let's have a look at what type of data will be fetched to a health authority server, and this is an example of iPhone user that the procedure is same for the other brands of the mobile phone too. So first is a user with exposure notification enabled on their phone. For this case, iPhone running iOS 13.7 or later, tested for COVID-19, and the test center or other health care provider determined that the user has positive test result and reports it to the public health center. And the PHA generate a verification code using the test verification service. The PHA sends this verification code to the user, and the code may be emailed, read over the phone, or provided as a linkable deep link or in any text message. The user enters this verification code or clicks the provided link to inform their phone of the positive diagnosis. If necessary, user iPhone prompts the user for additional information. Then the user iPhone creates a hashed message authentication, HMAC, calculated from user exposure key data and send it to the test verification server along with the user authentication token, receiving in return a certificate and additional per key metadata. So the user phone validates the returned certificate and metadata and store them. Then the phone prompts the user for permission to submit their key to the key server. And if the user grants the permission, their iPhone upload their temporary exposure key or TEK to the key server along with the authentication token, certificate, and metadata received from the test verification service. If the test verification service validates the uploaded key, it adds them to the database and returns a revision token that can be used to upload a diagnosis change for the uploaded keys. And at the end, the validated and uploaded key are available for download by other devices to be used for on-device exposure detection only. So what we have learned until here is the majority of the users who are using the applications, they are all the information, and there is no actual information of a person, or they are contacting with the other phones, and everything reside on a phone. Just in case a positive case happened, this was the procedure for that person only. So the privacy measures taken here is interesting too. So the key schedule is fixed and defined by operating system component, preventing application from including a static or predictable information that could be used for the tracking. A TEK is required to correlate between users' RPI, and this reduces the risk of privacy losses from broadcasting the identifier. Without the release of TEKs, it is computationally infeasible for an attacker to find a collision on a RPI. So this prevents a wide range of reply and impersonated attacks. And when reporting the diagnosis key, the correlation of these RPIs by others is limited to 24 hours period due to the use of this TEK, and this will change daily. And the server must retain the metadata from client uploading this diagnosis key after including those key in the aggregated list of diagnosis key per day. All right, so we just investigate a bit about the whole process of how they broadcast, how they scan, how they receive, how they generate these keys, how they communicate these keys, the nature of these keys. And all that being said, as described, this RPI and TEK generated by the app are design feature whose purpose is to reduce the risk of re-identification to near zero. So they are not directly identifiable. And of these elements, only the TEK are stored on the key server, and only when an individual has tested positive and chooses to upload this information. So to elaborate, the RPI are meant to be public by design. They are shared to other devices via Bluetooth, and as such do not provide any form of identifying information in the absence of of other information. So even if an RPI were intercepted by a device operator, by a malicious actor, it would be a meaningless number on its own and would not be linkable to any device without significant effort. So what does that mean? So there is a very unlikely risk that a highly motivated attacker could use something called a linkage attack. And by placing Bluetooth collection devices at various locations throughout the city, for example, at every road intersection, they could collect this RPI of passerby if attacker could recreate a device path through the city. So that being said, is to effectively track somebody's path, an attacker would have to have numerous collection devices deployed at significant density throughout an entire geographical region. So such an attack is possible, but requires an extensive resources and expertise to implement. And the chance of such an attack being successful is even lower, given that there is a high chance of the attacker being caught. So at conclusion, we try to see how many of these options this application picked, and what we have seen is, so the design and implementation of the app was subject to open independent expert review by software security and privacy expert in advance of the development, and the performance of the app and its effectiveness will be closely monitored and assessed as more Canadians begin to use it. The app is developed using the simplest approach possible to facilitate a timely and verifiable review of the implementation. The app only provides the necessary functionality to allow for contact tracing, and there is no additional code incorporated into the app. There is no secondary purpose embedded in the app. The only data collected are what is required for contact tracing purpose only. So all the other information are retained on the user device where they are stored and only shared with other users or to central repository if required for a contact tracing incident, as we saw. It is unlikely that any personal information will be collected by Government of Canada as part of the app, and the data that is collected is generally retained for a short period of time with purpose of supporting security measures. So in other words, it's like all the information in this application ecosystem is designed to be kept for the shortest time period necessary and to achieve the specific need the information is for. Use of the app is obviously entirely voluntarily in Canada. If users have been diagnosed with COVID-19, they will also be required to provide consent for their TEKs to be uploaded and made available to other users of the applications. And note that no personal identifiable information is sent to other users. They are only notified in case they have been exposed to the COVID-19 once they downloaded the corresponding diagnosis key from the key server. The app is unlikely to involve the collection of any personal identifiable information. The data collected via the app by the Government of Canada is limited, and as much as I could find, there is not a serious possibility of re-identification. Users who download the application will be required to review and accept a clear and accessible statement that provides them with information about how the application works, how information about exposure will be received by the user and transmitted to the mobile phones of the other users, and what data will be collected about them and how the data will be used and where it will be stored. So the privacy analysis, we could actually find so many privacy analyses available, and the privacy analyses are available right now of different stages. And the app as the whole will be shut down within 30 days of a declaration by the Chief Public Health Officer of Canada that the pandemic is over. So 30 days after pandemic is over, everything will be removed. And as well, individual can delete the application at any time, and the TEK on the devices delete after 14 days. And in other words, all the information in this application ecosystem is designed to be kept for the shortest amount of time period to achieve this specific need of information. So what I could find, what my research shows, and what after testing this application a bit, I found I could achieve is this application is totally privacy protected. No personal data, no identifier, no geolocation data, nothing personal are collected. And the application is completely open source in Canada, which helped us to look under the hood. And from what I could find in the Apple and Google technical report, this app is totally under control of the user. I hope this short presentation can convince anyone who are against this application in terms of privacy or security concerns. There are some other concerns, like some people with older version of the devices cannot use, which that is a different argument. And thank you very much. If there is any question, I will be happy to answer.
Thank you very much, Sajjad.